This is the second video, of course, going through this basic problem with reaction to cable spun, or a cable spun hung 200 feet. This is A, this is B. There is a 300-pound weight hanging at this geometry. It is 54.36 down, 74.23 over. There is a 100-pound weight. It's over here. It is hung there at that distance. We do not know its location. That is generally how these problems present themselves. They're kind of adaptives. This shape will assume the shape of the moment curve, and we'll talk about what the moment curve would be. Basically, it's a shape that if you flipped it up that and apply the same load, that arch would be under no bending stress. So it's a pretty efficient, it's the most efficient shape, if you would. So that said, I've solved out the problems here. We have to look at this logically and know that there should be more weight on A than B, and we move on to the next step. The next step is basically realizing that you can solve for the reaction at A in the X and because of your friend trigonometry. Now, you don't have to do it by trigonometry. You can just do it by drafting it. And so I won't do that here, but I'll demonstrate real quick. If in fact you're in CAD and you know that this up force, right, that up force is 214.7, and you know the angle of the cable because it's the same as this angle here, you can push this out and then get the horizontal component. However, you can also do it by realizing that there is some geometry of this angle being the same as this angle. Complementary, equal, and opposite. I don't know if they're complementary or supplementary. So I'm going to go ahead and pull out my little eraser here, just figuring out that that works pretty nicely. And so let's find out what that angle is. Well, it's the arctangent of 54.136 over 74.225. So we're going to go with this angle here, right? The angle at B equals the arctangent of opposite over adjacent, opposite being 54.136 and adjacent being 74.225. But if we really want to be smart about it, we want to get the direction of the cable. And the direction of the cable is actually change in y a minus 54.136, and it's a positive 74.225. And this is nuanced, so you don't have to do it this way, but remember we want to keep directions, not angles, generally in this. So we can run over here to our calculator, turn it on, of course check the mode. Look at that, I'm not even, I'm training you badly now, but the fact is the mode is an allegory, or I'm going to go second quit. We can also do 40 clear, hit the tangent of 45 degrees, and you notice this problem was not sketched up with some 3, 4, 5 triangle. I just sketched around a situation which we can then look at a little bit and sketch up in other different programs. So now what we want to do is we want to take the arctangent, and we're going to take minus 54.136 divided by 74.225. Hard to punch. Close it up, hit a return, and you have an angle of a minus 36.105. Of course, I like to do those positive, but I'm going to capitulate and realize that probably minus is fine. And so I'm going to put a minus 36.10. Why? Sometimes you don't want to capitulate, or that's equal to, I'm sorry, I got to do it. So second answer, plus 180, plus 2, minus 2. And if you're in the negative angles, that plus 2, minus 2 doesn't necessarily work. So that's 143 plus 180 equals 323.989. So this is also equal to 323.89, and that means going to mean we're going to know eventually the reverse azimuth. We're going to know going back the other way. So that's the angle theta here. That is my theta. So the direction of that cable is either 323.89 or the opposite direction, which is 143.89. So how do we use that? Well, we know the tangent of the angle is also equal to the tangent of the angle is also equal to f of y over f of x. The tangent of theta is also equal to f of y over s of x. So if we know this direction here is 143 point, which we said is 143.89, we know the tangent of 143.89 equals the force in the y direction, which we've already determined was 214.7 over the force in the x direction. And this, in case, is one of those ones we know what the force is in. So if we do it this way, the sign will come out. We don't necessarily do it this way in all reality. But we get the f of x, or the horizontal component of the tension, is going to be 214.7 divided by the tangent of 143.89. So you can do this all kinds of different ways. I'm just doing it with my calculator now here on my hand. 214.7 divided by the tangent of 143.89, and it should get me a negative number in the order of 294.32. So that now is in fact equals minus 294.32. And what we would see is this cable, right, as it got tauter and tauter and tauter, it would continue to have this same basic geometry. It would be similar shapes, but as the forces got up, you know, this would get closer and closer to the horizontal. So that's what's odd about that. So what I'm going to do now here is 294.32. I'm going to go ahead and pause here and clean this up, what I scribbled up, and stick it up here, and so we can move on. And what we have to realize is that the force is 294.32 here. It's 294.32 here. We'll get a check in this problem when we finally get to that reaction, and it does turn out to be the same as the cable. So the force in the x is 294.32 going outwards. I'm going to hit pause and clean this up. All right, here's what that looks like then. If you're looking above here, and hopefully you can move and zoom in with your calculators, or with your computers. But here, go back to review here, start inking here. Now, you get the geometry of that force by the geometry of the cable. And so in the end, you know that this cable has a direction this way of minus 36 and this way of 143.58. Now the 143.58 is opposite of the cable, and that, of course, at this reaction is what the reaction has to be equal and opposite to the cable. So once you know that force here, you can go down to this bit, the next point, which is the point on which the force is hung, and you can draw a free body diagram. You kind of ignore everything else, and you go down to here and you say, well, that's 300 pounds in that direction. And this, you eventually know the direction, but in the end, you can just know the components. The components then are just going to be 291 in that direction. And going up, of course, it will be 214.70, ignoring, of course, the weight of the cable, which you do in these problems. So the reaction is 214.70. Now, you're much better off just calculating, I think, the tension in the cable, knowing the geometry, and then doing, of course, the basic, adding your forces, 1, 2, and the third one, whatever the case would be, has to be then the reaction in the other cable. So we're going to do it that way. What we're going to do here mathematically is we're going to do that mathematically that way, And we'll finish up in the next section with that. But let's look real quick why CAD is so great on that. And that would be, in fact, if you were here and you could go to this cable here and you could draft 300 down, and you could draft this to scale, and it would be a lot more than 300. You could add this vector. Remember how you take this one, move it down? And then what this remaining vector would have to be the cable, the other cable. And then you could just go over here and just start that going the other direction. You would also know its magnitude and its force. When you went to here, you could do it again. This time it would be 100 down. And it would be a tension this way, and then you'd have to come up with that. Thanks for listening. We'll finish this up in the next one.